let's take a look at NYJC paper 2 2019 for their prelim. This is what they have last year, and we are going to zoom in directly to section B. So that will be question number 5. Okay, and as I was saying, for some of you who are just joining, my suggestion is to start with statistics first for a prelim paper 2. So so that's what we are trying to do today. Okay. Okay. For Alvin, right? I assume you're talking about the playback for the live stream. I see some of you have already gotten an access to the playback for the live streams that we have every week. For the second part of ACJC, I think probably like later today or tomorrow, we should probably be able to publish that paper with the live stream, for the second part of ACJC paper 1. Okay, so probably I think latest tomorrow it should be published. So Alvin, you should be able to see it by tomorrow, hopefully. Okay, anyway, let's start with this question number 5. It is a P&C question. We have the word statistics. We have the word addressee that is given to us. Let's try to reorganize these few letters. So we have 1A, then D, R, E, S, then E. Okay, so 2 Ds and 3 Es. Part 1. A super easy part. I want to find the number of different arrangement for the 9 letters that we have here. So for the 9 letters, it is going to be 9 factorial. Then 2 Ds, so divided by 2 factorial. And 3 Es divided by 3 factorial. 2 S's, so divided by 2 factorial. This is going to be equal to 15120. Super easy, 1 mark. Part 2. Part 2, we want to find the number of different arrangements such that both D's are together and both S's are together. So we are talking about A, D, D, that both D's are together. Then R, E, S, S, these 2 S's are together. Then E. So we have 1, 2, 3, 4, 5, 6, 7. So it is going to be 7 factorial. As for the 3 E's, we are going to be dividing it by 3 factorial. And this gives me 840. We will not need to permutate these 2 D's and 2 S's because they are identical. Even if you plan to permutate these 2 D's or 2 S's, it is going to be 7 factorial. Then divided by 3 factorial, which is what we have gotten here. Permutating these 2 D's, it is going to be 2 factorial. Since they are identical, we will still be dividing it by 2 factorial. The same for 2 S's, so 2 factorial divided by 2 factorial. So they will be sort of like invisible. That's why it is not super necessary for us to actually write down the permutation for the 2 D's or the permutation for the 2 S's. This is part 2, and let's take a look at part 3. Part 3, I want to find the number of different arrangements that can be made when the E's are separated. So we're going to use slotting, but separated by at least 1 letters, and the D's are supposed to be together. So I'm going to look at A, D, D. The 2 D's are supposed to be together. Then R, S. So if you are looking at this 1, 2, 3, 4, it is going to be RSS, there are 2 S's. So 1, 2, 3, 4, 5. It is going to be 5 factorial. And the 2 S's, so divided by 2 factorial. It is not necessary for us to permutate the 2 D's because it is going to be the same as this. It will be 2 factorial divided by 2 factorial anyway. So to make sure that the E's are separated, we are going to make use of slotting. So here are where we can slot the 2 E's, and let's not forget the 2 N's, which will be here and here. So 1, 2, 3, 4, 5, 6. It is going to be out of 6, we will choose 3 for the 3 E's. It is not necessary to write down a 3 factorial for the 3 e's because they are identical. So even if you to be writing down the 3 factorial, you'll be dividing it by 3 factorial anyway. So this, it will give us our answer 1, 2, 0, 0. So part 1, part 2, part 3, I will say that they have given us a good warm-up to starting section B. But part 4 is surprisingly very tedious. I was a little bit surprised because at a glance, I don't know what you guys what's your first thought when you see something that is like part 4. We want to find the number of arrangements such that the e's are not together, the s's are not together, and the d's are not together. So my very first impression is, how about doing a 1, 5, 1, 2, 0, since this is all the possible arrangement of the word addressee. So how about taking this 1, 5, 1, 2, 0, and I will just minus away the case where the e's are together, the s's are together, and the d's are together. Okay, so that was my first impression. But isn't it a little bit too easy for 4 marks question? So let us try to get the correct perspective for this question. Okay, so one good way for us to look at this question is actually to try to make use of a Venn diagram. So if I were to try to list down 3 events, for example, event D, I'm going to call event D as for the D's to be together. So for event D, it will be when D's are together. Yep. If I were to be doing it this way, 1, 5, 1, 2, 0, minus away the case where all the e's are together, all the s's are together, all the d's are together, it is not going to work. Okay, actually the marks that is allocated already told us that it is probably more complicated than that. So anyway, let us try to get a good perspective of what exactly this question is trying to ask us. Okay, to go for the case where all the e's are together, all the s's are together, and all the d's are together. So D, it represents the event where all the d's are together. And for E, I'm going to go for all the e's are together. So e's are together. And S is where all the letters S are together. So what this question is asking for is something that is not inside E, not inside S, and not inside D at the same time. Which means that if I were to try to view this on a Venn diagram, so if let's say event D is here, let's say we have event E and event S. Okay, let's say we have these events. That means what this question is asking for is the number of ways such that it is outside D and outside E and outside S at the same time. Which means that what the question was asking for is actually this portion here. Really all this portion. Where this area here is representing what that is outside D, outside E, and outside S at the same time. Okay, which is what this question is asking for. So what I'm thinking of, okay, it is I'm going to try to take this, which is the universal set. It is everything minus away. I'm going to minus away the number of events that is in D or E or S. So I'm going to minus away this region here. Okay, I'm going to take this, minus away this region. So let's try to work out this region first. And I think I'm going to try to work on, okay, let me erase this. So I'm going to try to work on first the number of arrangements where the D's are together or the E's are together. Okay, I'm going to try to work on this region here. So for this region here, let me just try to shade it. Okay, so okay, it's okay. Let's just imagine. Okay, for this region here. So for this region here, it is going to be the number of arrangements such that it is going to be in D, plus number of arrangements such that it is going to be E, minus away the number of arrangements such that it is D and E. We are using the we are using the formula for union. So it's this plus this minus away the overlapping. As for this means that the D's are together. So we are looking at A, D, D, R, E, S, S, E, E, where the D's are together. As for this is when the E's are together. So this is A, D, D, R, S, S, E, E, E. So we want to make sure that the E's are together. And for this, it is A, D, D, the D's must be together, and R, S, S, E, E, E. So the E's must be together. And I'm doing this based on what I visually see on the Venn diagram. It is a very, very good tool for us to be analyzing probabilities and to be analyzing P&C for cases that is like this, part 4. So this, for the D's to be together, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 objects, so arranging all of them, 8 factorial. Then we have we have 2 S's, so divided by 2 factorial. We have 3 E's, so divided by 3 factorial. As for the 2 D's, okay, I'm not going to touch them at all because it is going to be 2 factorial divided by 2 factorial anyway. Then plus event E, it is when the E's are together. I have 1, 2, 3, 4, 5, 6, 7. 7 objects, so 7 factorial divided by 2 D's divided by 2 S's. As for the E, I'm going to leave them as it is because it is going to be 3 factorial divided by 3 factorial. As for this, it is 1, 2, 3, 4, 5, 6. So we have a 6 factorial divided by 2 S's, so divided by 2 factorial. And this is going to give us a 4, 2, 6, 0. Then I'm going to try to find, because we have already gotten this region, let me use yellow color. Okay, so we have already found this region here. And now we are going to try to find this region. Okay, so to find this red colored region here, it is what that must be inside S, and it must be outside D, and it must be outside E, correct? If I were to use Venn diagram set notation to represent this red colored region, inside S and outside D and outside E. And I guess in order for me to do this, I'm going to take everything that is inside S. I'll take this whole thing. Maybe I can do a quick sketch. So this is S. So I'm going to take this and I am going to minus away whatever that is in D and in S. So I'm going to minus away this region here. I'm going to minus away this region here in D and in S. So I'm going to minus away D and S. So minus the number of ways to get something that is where all the D's are together and all the S's are together. Then I'll minus away this other region here. And that means I'll minus away this region here. And this region here, I am going to do this. I'm going to take all the events that are inside E and inside S. Then I'll minus away this region where all the D, E, S are overlapping. So D and E and S. Okay. So I'm just trying to find ways to piece the areas together. So let me repeat this one. I'm trying to look for this area here, and that area is this region here. Okay, so to find this region, we're going to take the entire thing, which is the number of events, the number of the number of arrangements that is where E's are together and S are together. So it is this entire region. Then I'll minus away this where all the three events are overlapping. So it is D and E and S. So for this, it is when all the S's are together. We have a D, D, R, E, S, S, E, E. All the S's are together. These D's and S are together. So we are looking at A, D, D. The D's are together. Then R, E, S, S, E, E. Then the S's are together. And for this is when the E's and the S are together. So we have a D, D, R, S, S. The S's are together. Then E, E, E. The E's are together. And finally, for this, it is when the D's are together, E's are together, and S's are together. So it is A, D, D. D's are together. R, S, S, S's are together. Then E, E, E. All the E's are together. And I think you get the idea, okay? It is repeating this numerically. For this, it is going to be 1, 2, 3, 4, 5, 6, 7, 8. We have 8 objects, so 8 factorial, divided by 2 D's, 2 identical objects, 2 factorial, 3 E's, divided by 3 factorial. We are ignoring the 2 S's because it is going to be 2 factorial divided by 2 factorial. Then we will minus away this case, 1, 2, 3, 4, 5, 6, 7. We have 7 objects, so 7 factorial, divided by 3 E's, so divided by 3 factorial. Then I will minus away this case. For this case, we have 1, 2, 3, 4, 5, 6 objects, so 6 factorial, 2 D's divided by 2 factorial. Then minus away this case, it is 1, 2, 3, 4, 5, just simply a 5 factorial. Ignoring the 2 D's because it's going to be 2 factorial divided by 2 factorial, ignoring the 2 S's, 2 factorial divided by 2 factorial, and 3 E's divided by 2 factorial divided by 3 factorial divided by 3 factorial. So this is going to give us a 2280. So the total number of ways that we are looking at, this is going to be equal to all the different possible ways, which is from here. And from part 1, we got our answer as 15120. Okay, so it is the answer from part 1. Then I'll minus away this case, which is 4260, and I'll minus away this case, which is 2280, and this is 8580. Okay, so this is for question number 5. I think it is still okay. You know why? Because at least part 1, part 2, and part 3, they are very simple. Part 4, the marks that is allocated remind us that it is not going to be a simple question. And at the same time, like what I've been telling my tuition class, we can try to find we can try to make use of tools that can help us to process the information that is given to us by the question for questions that is related to P&C and for probability. We can use tools like, for example, using a grid that can help us to list down all the possible outcome. We can try to make use of probability trees to try to organize those kind of stages kind of questions for probability. We can use Venn diagram. We can definitely also try to make use of P&C within a probability question. All these tools actually helps us to process question like way better. For example, for a question that is like 5 part 4, without the Venn diagram, I seriously think it is going to be very difficult, for most of us to be able to mentally process something that is like this and like this. Okay. Yeah, in fact, I do not want to bluff you also, okay? It took me a while to sort of like get this question. It is not like instantly I've got this, because I was telling you the first instance when I saw this question, I actually thought, okay, it is most likely going to be a 15120, which was from part 1. Then minus away like D's are together and E's are together and S are together, which is actually just this overlapping region. But trying to get my perspective from the Venn diagram, I know that it is not going to be just this overlapping region, but You know, it is actually this what do you call this, like this flower thing. Okay, so this is question number 5. Let's move on to question number 6. I think for me, question number 5, part 4 is probably the hardest in section B. Question 6 is pretty okay. Okay, and this reminds us why we should really start with statistics first as a strategy for us to be tackling our prelim and to be tackling our A levels. So question number 6. We are looking at flares that are 1 year old, 5 years old, and 10 years old. With the probability of them successfully firing are given to us here. Part 1, I want to find the probability that out of 100 1-year-old flares, at most 2 fail to fire successfully. So I'm going to write down my random variable. I'm going to go for X. One-year-old flare. Because we are looking at those that fail, so I'm going to go for 1-year-old flare that fails. That fail out of 100. So what do we see here? We see a binomial distribution. We see a binomial distribution. There are a total of 100 1-year-old flares. And the probability of the flare being, failing to fire, it will be 1 minus. For 1-year-old, the probability of success is 0.995. So this minus 0.995 is going to be my probability distribution for part 1. So it will be a binomial distribution. Out of 100, this is 0.005. So we are trying to calculate the probability where X is supposed to be at most 2 failures. So X is supposed to be less than or equal to 2. And if I were to press this into my Texas Instrument calculator using binomial CDF, by using binomial CDF, this is equal to 0.986. Okay. Really? If you are going for success, I don't think it is going to be so, right? At most 2 failures. So if I'm going for success, if we go for success, that means we are going for a binomial distribution of 100 and 0.995. And we are looking at most 2 failures, which means that we are talking about, let's say we are talking about success. So if there were to be at most 2 failures, that means the success must be bigger or equal to 98, right? So it will be calculated as 1 minus probability that S is less than or equal to 97. At most 2 successes. Yeah, I think it should be this. I don't think it is going to get a 0, right? Yeah, I don't think it is going to. It should give you exactly the same answer. Maybe you can just try to press the GC again, right? I think this should be fine. Okay, the strategy that you are working on shouldn't be a problem. Next, part 2. Okay, so part 2. Part 2, we are talking about 1-year-old flares packed in boxes of 100. Hey, we have 100 1-year-old flares here. So each of these are going to be packed in boxes, and we are talking about, how many boxes are we talking about? We are talking about 50 boxes. Okay, so these 100 flares are going to be packed into boxes of 50. and we want to look at those boxes with at most 2 flares that will fail. So one box is going to have 100 one-year-old flares. At most 2 flares will fail, so this is going to be the probability. This is the probability where in one box there will be at most 2 flares that will fail. So let me define my new random variable. I'll let y number of boxes of 1-year-old flares. With at most 2 flares that fail. We are talking about this out of 50 boxes. So y here should also follow a binomial distribution. You should follow a binomial distribution with out of 50 boxes. The probability that with the probability that in one box there is at most 2 flares that fail, it is going to be from part 1. And I'm going to write this to 5SF, so 0.98590. And according to the question, there should not be more than 48. What is the probability? So we are talking about y to be less than or equal to 48. Okay, and if I were to press this into my calculator, this is 0.157. Okay, I think it is still quite an okay and easy question. Let's continue. Part 3. Part 3. We have now 7 flares with a mixture of 5 years old, and 10 years old flares. There is 1 5-year-old and 6 10 years old. I want to find the probability that in part A, that the 5-year-old will be successfully fired and at least 4 of the 10-year-old flares are going to be successfully fired. So for the 6 10-year-old flares, I'm going to go for another random variable to represent those that are successfully fired. Let me go for W. Number of 10-year-old flares that fire successfully. And this time we are talking about 6 such flares. So W here is going to be another binomial distribution. Total, we are talking about 6 of them, and the probability that it is going to, a 10-year-old flare is going to be successfully fired is 0.750. So the required probability here is going to be the 5-year-old flare fails to fire successfully. So 1 minus the probability of the 5-year-old successfully being fired is 0.970. So the 5-year-old fail, and for the 10-year-old, at least 4 of them are going to be fired successfully. So it is probability when W here is bigger or equal to 4. So this is 1 minus 0.970. And to press this into the calculator, we will go for 1 minus probability that W is less than or equal to 3. Because we want 4, 5, 6. So we minus away less than or equal to 3. If I were to press this into the calculator, the answer should be a 0.0249. Next, part B. Part B, let me write it down here, okay? So 3B. 3B, at least 4 of the 7 flares are supposed to be fired successfully. The required probability is such that at least 4 of the 7 flares are successfully fired. Actually, we have one of the possible cases here, right? This is when the 5-year-old flare fail, and at least 4 of the 10-year-old flares are successfully fired. So this is already one of the cases for part B, and the probability is this. Okay, I'm going to write it in 5 significant figures. That will be 0.024917. Okay, so this is from my answer that is here is from part 3A. And this is when the 5-year-old flare failed. So what if the 5-year-old flare was successfully fired? That will be this. And there must be at least 4 of the 7 flares failed successfully fired. So the 5-year-old is already successfully fired. So for the 10-year-old flare, at least 3 of them should be successfully fired also. So this is going to be 0.024917 plus 0.970. As for this, to calculate this using this binomial distribution, it is going to be 1 minus probability that W is less than or equal to 2. Okay, because we want 3, 4, 5, 6, so we will minus away less than or equal to 2 so that we can press into a calculator binomial CDF. This will give us a 0.958. Pretty okay question, I think. Question number 6. Next, let's take a look at question number 7. So we have done a P&C question. We have done a binomial distribution question. And question number 7 is a normal distribution question. Okay, this question. It is also a pretty okay question. It's just a little bit tedious. But it is definitely those questions if I were to start my statistics first. Okay, it is definitely those kind of questions that I'll probably be able to score. So far, we have done, this is the 3rd question. And there should be just one part that I think most people will not be able to get to like too many marks, which is question number 5, the last part. Okay, for the rest of the parts, all the way until this particular question, I think we should aim to score as high as possible. Okay, so we have now 2 cashiers and they are going to be serving customers. According to the question, the time taken to serve a customer is going to follow a normal distribution with a mean of 150 seconds and a standard deviation of 45 seconds. Part 1. I'm going to let X be the time taken to serve a customer. So let me write down my random variable. Serve a customer. So according to the question, X follows a normal distribution with the mean of 150 and a standard deviation of 45. So we have a 45 square here. Goodness, part 1 is extremely easy. We are just trying to find the probability that the time taken for the cashier to serve a customer is more than 180. So lower limit 180, upper limit E 99. Then we press in the parameters 150 and 45. This will give us a 0.253. Part 2. One of the 2 cashiers will be serving 2 customers one after another. By stating a necessary assumption, because we are going to be looking at the total time, right? The question says the total time for the cashier to be serving these 2 customers. So we are talking about x1 plus x2. So we are going to assume we are going to be doing linear combination x1 plus x2. So we will be assuming that for the time taken to serve 1 customer is independent of the time taken to serve another customer. So that is the assumption. Assume that to serve to serve a customer is independent of the time taken to serve another. Okay, and we are looking at x1 plus x2, the total time that is taken to serve two customers one after another. So let's try to find the expectation of x1 plus x2. This will be 2 times the expectation of x, which means that it is going to be 2 times of 150. This is equal to 300. And we want to look at the variance also of x1 plus x2. And this is 2 times the variance of x. So it's going to be 2 times of 45 square. 2 times of 45 square, this is 4050. So now we have a linear combination of 2 different instances of x, where x is the time taken to serve a customer. So we have the total time taken to serve 2 customers when they are linearly combined together, when each individual of them is a normal distribution. Linearly combining them together will also follow a normal distribution with a mean of 300 and a variance of 4050. And we're trying to find the probability that it is going to take less than 20 seconds to serve these 2 customers. So it is going to be when x1 plus x2, this is less than 200. And this, according to my calculator, is 0.0581. The answer for part 1 is 0. Oh, yeah, you are right, Ben. Okay, you're right, Ben. So, so this is 0.252. For the last part of question number 6, question number 6, part 3b. Question number 6, part 3b, the answer is 0.958. Okay, next let's look at part 3. Part 3 is just very tedious also, but it is definitely not difficult. We are still going to be letting x be the, I'm going to be letting x be the time that is taken for the first cashier to be serving the customer. So for this first cashier, the first cashier is going to be serving 4 customers. So I'm going to let, for example, A be the total time taken to serve the 4 customers by the first cashier. So we're talking about x1 plus x2 plus x3 all the way until x4. I'm doing part 3 here. So we can find the expectation of A. This is going to be expectation of x1 plus x2 plus x3 all the way until x4, and that will be 4 times the expectation of x. So it is 4 times of 150. This is equal to 600. And we are going to find the variance of A, which is 4 times the variance of x. And in case you guys forget what is x, x represents the time taken to serve a customer. So x follows a normal distribution with a mean of 150 and 45 square as the variance. So I'm going to go for x to be the time taken by the first cashier. Okay, so A represents the total time by the first cashier to be serving 4 customers here. So variance is going to be 4 times of 45 square. And this is equal to 8100. So A is going to follow a normal distribution of 600 and 8100. As for the second cashier, so x is for the first cashier. For the second cashier, I'm going to go for a new random variable, let's say y. I'm going to let y be the time taken to serve a customer, by the second cashier. Oops. The second cashier. So y will also follow a normal distribution with a mean of 150 and a variance of 45 square. And for the second cashier, this person is going to be serving 3 customers. So we are talking about y1 plus y2 plus y3. And I'm going to let b be this y1 plus y2 plus y3. So the expectation of b is going to be 3 times the expectation of y. So it's 3 times of 150. This is equal to 450. And as for the variance of b, this is going to be 3 times the variance of y. So it's going to be 3 times of 45 square. And this is equal to 6075. So this tells me that for b, it will also follow a normal distribution. And this time, this normal distribution has a mean of 450 and a variance of 6075. So according to this question, we are supposed to find the probability where the total time taken by the first, we're going to find the probability that the first, the 4 customers at the first queue, which is served by the first cashier, is they will be served before the 3 customers served by the second cashier, which means that the total time taken by the first 4 customers should be less than the total time taken for the 3 customers, so that they will all be served before the 3 customers. So to find the probability of this, we are going to look at this as probability of A minus B to be less than 0. So we have the probability distribution for A, we have the probability distribution for B. Okay, so we will find A minus B. We will try to find a distribution for A minus B. So the expectation of A minus B, it is the expectation of A minus away the expectation of B. Expectation of A, this is 600, minus away 450. So the expectation of A minus B is equal to 150. And we will find the variance of A minus B. I don't get it. What should I be laughing at? Then this is variance of A plus the variance of B. So this is equal to 8100 plus 6075. This is equal to 14175. This tells me that A minus B, this follows a normal distribution of 150 and 14175. And I'm going to just make use of this, pressing into the calculator for this probability here. So from my calculator, this is equal to 0.104. Okay, still a pretty easy question, I guess. It reaffirms to us that starting off with statistics is a very good idea, which means that most likely we will be able to score higher if I can start with all these easier to score questions first. Okay, next, the next one is question 8, which is a correlation linear regression question. We are going to be skipping that since it's not tested, since we are not going to be tested for our A levels. Let's go for question number 9, then 10. 9 is a discrete random variable question. Why? The mean is expectation of A minus away expectation of B, right? Just now we did it. The mean is expectation of A minus away the expectation of B. Then expectation of A is 600 minus away the expectation of B, which is 450. So it should be positive 150. That is correct. We just now we had a as one that follows a normal distribution of this is 600, right? Then B follows a normal distribution. This is 450. Since we are looking at A minus B, so the expectation of A minus B is going to be 600 minus 450. So this is 150. I mean, if you are using B minus A, I guess that will be minus 150. But if it is A minus B, this should be okay. Hey, but you think about it from another perspective, okay? It is just tedious, but it's actually so easy to do. You know, so we should definitely try to make use of statistics to our advantage. Furthermore, for most of you, even if you are not doing a lot of math in your university, very likely you will still be doing statistics. You know, for econs, for a lot of humans subjects, you will still come back to statistics anyway. So I do have quite a few students, you know, who after they have started university, then came back to me and asked me, you know, can I give them, you know, some of the materials that we have done the last time for statistics, because they realize that what you guys have been using for statistics in your JC, right, is actually a very, very good resource for your university. Okay, we are skipping 8. Let's move on to question number 9. A discrete random variable question. So for question number 9, we have 18 cards. They are numbered 1 to 6. Each number is going to be appearing 3 times. So 3 1s, 3 2s, and so on, all the way until 3 6. A player is going to draw 3 cards without replacement. X is the number of cards with the same number. So part 1, we want to find the probability that X is equal to 2. So if X is the number of cards with the same number, we are talking about for the 3 cards that are drawn, there are 2 cards that are of the same numbers. And if the 2 cards are of the same numbers, we are talking about these scenarios that is like this. We are talking about scenario that is like having a let's say A, B, 2 cards of the same number, or we are talking about something that is like A, B, A, or it can be something that is like B, A. Okay, where 3 cards, where out of 3 cards, 2 of them are of the same numbers. So if it is this case, for the first card, it can be anything. So it doesn't really matter, 18 out of 18. For the second card, it must be the same as the first card. And for each card, for each number, it's going to appear 3 times. So so that number has already been obtained during the very first draw. That means for the second draw to be the same as the first draw, the chances will be 2 out of 17 since there's no replacement. As for the last draw, it cannot be the same as this card. So these 2 cards, they are the same number, which means that there will be 15 other cards that are of different numbers. So 15 as in like 18 minus 3. Okay, so it will be this divided by 16. And let me very quickly explain it one more time. So the first card, it can be any card, so 18 out of 18. The second card must be the same as the first card according to the case that we are looking at. So for the second card to be the same as the first card, the probability is 2 out of 17 because each number is going to be appearing 3 times. So whichever number that was already drawn, there are 2 of them left. So 2 out of 17 cards in total left. Then for the third draw, it cannot be the same as the number that is drawn in the first 2 cards, which means that there will be 15 other cards that are not the number that is from the first 2 cards. So 15 out of 16. Or if it were to be this case, the first card, it can be anything. So 18 out of 18. The second card cannot be the same as the first card. So that will be 15 out of 17. And the last card must be the same as the first card. So that will be 2 out of 16. Similarly for this, the first card can be anything. So 18 out of 18. The second card cannot be the same as the first card, so this will be 15 out of 17. And the last card must be the same as the second card, so that will be 2 out of 16. Or if you can really see, this is basically just 18 out of 18 multiply by 2 over 17 multiply by 15 over 16. Then you can either just simply multiply it by 3 or multiply it by 3 factorial divided by 2 factorial. Your answer here should be a 45 over 136. And we are supposed to determine the probability distribution. Okay, I don't really get what you mean by 3 cards that is labeled 2. X is equal to 2 is not cards that are labeled 2. According to the question, X represents the number of cards that are of the same number. So X is equal to 2 represents that there are 2 cards that are of the same number. It is not number 2 that appears. It is 2 cards that are of the same numbers. For example, if I were to be looking at probability that X is equal to 0, that means there are 0 cards that are of the same number, which means that the first card, it can be anything, so 18 over 18. The second card cannot be the same as the first card, so that will be 15 out of 17. And then the third card cannot be the same as the first 2 cards, which are already different, so 18 minus 3 minus 3, we have a 12, so 12 out of 16. And this is equal to 45 over 68. And we have one last case, that is when all the 3 cards are the same. So for all the 3 cards are the same, I can take 1 minus this. Or if we were to calculate it from scratch, the first card can be anything. The second card must be the same as the first card, so 2 out of 17. And the last card must be the same as the first 2 cards, which will be 1 out of 16. This is equal to 1 over 136. Let me draw my probability distribution table here. We'll be making use of it. So X and the probability when X is equal to X. So X can be 0, 2, 3. When X is equal to 0, the probability is 45 over 68. For 2, this is 45 over 136. And for X is equal to 3, this is 1 over 136. Okay, this is part 1. And I guess part 2 is like really simple. I would suggest for some of you who have access to the videos on the theory outline, take a look at the derivation for expectation and variance. I think it is going to be very, very helpful for not just the understanding, but just in case this year A-level did a little bit of twist and asked you about the idea of expectation and variance instead of just the numerical calculation, I do think that the videos are going to help a lot. So for the expectation of X, this is going to be summation of X, probability that X is equal to X. So this is equal to X will be 0 multiplied by 45 over 68 plus 2 multiplied by 45 over 136, then plus 3, then multiply by 1 over 136. So the expectation is equal to 93 over 136. And nope, you cannot write X to be equal to 1 instead of 0. You must write X to be equal to 0. Because what is X again? X represents the number of cards with the same number. You cannot have 1 card with the same number. With the same number, you need at least 2 cards. Or of course, if there were to be no cards that are of the same number, then X must be equal to 0. Because there's no cards that are of the same number. Or you cannot write it as 1. If you write it as 1, then the expectation is going to be incorrect. I mean, it is like saying, I have 1 card with the same number, So that is not very logical, right? But if I have no cards, 0. I have no cards that are of the same number. Yeah, that is that is more that is more logical. So next, I'm going to find expectation of x squared, which is going to be expectation of x squared, probability that x is equal to x. Oh, talking about the x is equal to 0, x is equal to 1. Okay, now that I think about it, I can understand why you will say 1. Okay, because when x is equal to 1, is like all the cards are different. That's why you want to say it as 1. But one thing that I stress a lot, during my tuition class is that when it comes to statistics, many times we should just try to recite the math using our day-to-day English, because our day-to-day English embodies a lot of common sense, a lot of logic. So if when you talk about it and it just feels sort of like weird, there's one card of the same number, then most likely the way that you are trying to write it down numerically, it is also going to be incorrect. Where, like for example, this case, in day-to-day English, you don't really talk about there's one card that is of the same number. Okay, so anyway, continue with this. We have a 0 squared multiplied by 45 over 68 plus 2 square, then 45 over 136, then 3 square, 1 over 136, and this is equal to, let me see, this is equal to 189 over 136. So this will help me to find the variance of x, that is expectation of x square minus away expectation of x square. So this is 189 over 136 minus away 93 over 136 square. The variance is going to be equal to 0.922. Then part, actually this is part 2. Then part 3. Part 3, we are talking about this game being played 40 times, and we are supposed to find the probability that the average number of cards with the same number is more than 1. The number of cards that are of the same number is x, and it is going to be played 40 times, so the average number of cards per game is going to be x1 plus x2 plus x3 all the way until x40, this divided by 40. So we are trying to find the probability that this average is going to be more than 1. And this has a notation in our syllabus. We can call it x bar. And x bar will follow a normal distribution with the mean of x. The mean of x is 93 over 136. Then the variance of x, which is this, I'm going to go for at least 5 significant figures. So this is 0.92209 divided by 40. Okay, divided by this. And since x since we don't really know what is the distribution of x, in order for us to be writing down this, we are making use of the fact that we are combining a lot of x's together. So we are writing this by approximation through the central limit theorem. Since n, which is 40, we are considering it as a number that is large enough for us to do the central limit approximation. And what the question is asking for is to find the probability when x bar is more than 1. So this, from my calculator, is 0.0187. With 0.0187. One mistake that I sometimes see students will commit when they press this into the calculator, where it is the failure to see x bar as just any other normal distribution. You cannot see x bar as a distribution where its standard deviation is like specifically this 0.92209. I mean, let's just see this x bar as y with a distribution as this. So just take note that sigma is going to be square root of this entire thing. It is not just the square root of 0.92209. If you have pressed this into a calculator, you should be able to get the answer as this. Okay. Next, let's look at part 4. Part 4, we are now looking at SAM's winning. SAM's winning, okay. I don't know why, it sounds a little bit weird. So, anyway, I'm going to let W be SAM's winning. You know, one thing that you should try to do is to try to deduce this. If you if you can just take a look at the derivation on the theory outline on Achevas TV under sampling theory, the deduction of this will immediately explain, because I do hear a lot of students, right? They probably like a lot of us, we were trying to memorize this as a formula. Let me just very quickly talk about this x bar thing, okay? We try very hard to memorize the formula for x bar. We know x bar has a formula. It will be normal distribution of, for example, mu and sigma square divided by n. I mean, it has this formula. Okay, so I'm applying it here. That's why I don't need to go, that's why I don't need to square or whatever to the 40. Okay, so it is the variance divided by the sample size, which is 40. Okay, but this formula by itself, it is very difficult to find a meaning to this formula. Okay, and that is what I think that is what I think you are trying to understand it. But you are looking too much at just the formula instead of the derivation. So my suggestion is go and check out Achevas, the theory outline on the Achevas TV. You will see this. Okay, let me just very quickly show you the derivation of this. The derivation makes this very, very obvious. Because for example, let's say x follows a normal distribution with mu and sigma square. Okay, let me erase this, okay? So let's say x follows a normal distribution of mu and sigma square, and we are looking at something that is like this case, where it is the average of n numbers of x. So we are talking about x1 plus x2 plus x3 all the way until xn divided by n. Okay, we are talking about this, which means that if I were to try to form, and this x bar here is this x1 plus x2 plus x3 all the way until xn divided by n. So my aim, right, is to get a distribution for this. Okay, so plus xn divided by n. And since x follows a normal distribution, I know when I combine these together, it will also form for me a normal distribution. So why not, for me to form this normal distribution, right? I'm going to try to find its expectation, and I'm going to try to find the variance of this entire thing. So the expectation of x1 plus x2 plus x3 all the way until xn divided by n, 1 over n is a constant, so 1 over n. Then we will have expectation of x1 plus x2 all the way until xn, so it is 1 over n, and this is n times the expectation of x. So cancel, this is going to be the expectation of x. And what is the expectation of x? Mu. So here is mu. Let's try to work out what is the variance of x1 plus x2 plus x3 all the way until xn divided by n. 1 over n is a constant. I'm going to take it out of the variance notation. So according to the rule, it is 1 over n square, which means that we will have a variance of x1 plus x2 plus x3 all the way until xn. So this is going to be 1 over n square, and this is n times variance of x. So n and n can be cancelled. We will be left with a variance of x divided by n, and variance of x is sigma square, right? Variance of x is sigma square, this divided by n. So here we have a sigma square over n, and this has a notation. The notation is x bar. So we apply it to a scenario that is like this, and we apply to a scenario that is like this case here. So it will be 93 over 136. Okay, and this is the expectation of x. Then it will be the 0.92209. So this is going to be the variance of x, then divided by 40. So this will follow a normal distribution of this. That is why it is 40. Okay, that is why it is 40, and it is not necessary for it to be 40 square. And just imagine together with me again, okay, if you were to just look at this and try to explain yourself based on this, it is very, very confusing. I would suggest that you quickly, the moment when you have a question on this, if you are confused by this formula, just very quickly go back to the derivation. Everything should become very, very clear. Okay, and for Joyce, as long as they are the same number, right, then it is considered as a winning, which means that if I were to build another probability distribution for W, it will be like, for example, W, then probability that W is equal to W. Okay, so for Joyce, right, we are talking about the person losing, that means minus A, right? The winnings will be minus A. Winning, it will be A plus 10. So to lose, it is when no cards are the same. So we have a 45 over 68. And for winning, it is when there are cards that are of the same number. So whether it is 2 cards or 3 cards, it is considered as winning. So we are talking about the probability as 45 over 136 plus 1 over 136, which means that we have a 46 over 136. And we are talking about the expected winning, so expectation of W. The expected winning is supposed to be positive, so this is supposed to be bigger than 0, which means that the summation of W and multiply by probability that W is equal to W. This must be more than 0. So minus A multiplied by 45 over 68. Then plus A plus 10 multiplied by 46 over 136. This must be bigger than 0. You'll be getting a minus 11 over 34A plus 115 over 34. This must be bigger than 0, so A is going to be less than 10.45. And since A is an integer value, we can also say that A is less than or equal to 10. But let's be a bit careful because A represents the amount of money that he has lost. So A shouldn't be 0. Then, what's the point of playing this game, right? And A shouldn't be a negative number, which means that if he loses, he's actually going to be getting money. So let's add in A to be strictly bigger than 0. Or since it's an integer value, we can also say that it is bigger or equal to 1. Okay, and if for part 3 you want to use the variance as 0.922, it is perfectly fine here because in the previous part of the question they ask you to prove that it is 0.922. If this part is missing, if you are supposed to find variance of x without showing, then I guess for part 3 we got to use 5 significant figures for variance instead of 0.922. Let's look at the last question, which is actually the longest question in this paper too. It is not a difficult question also. So hypothesis testing, which is what I think most of you should have been, should be doing it as the last topic in your school, right? Hypothesis testing. Let's take a look at this hypothesis testing question. So we are talking about a coating that is on this computer part, where the coating should be 100 microns thick. It cannot be too, according to this question, it shouldn't be too thin. It cannot be too thick. So it must be this 100 microns thick. And the average is 100 microns and the standard deviation is 10 microns. If it is not too thin or too thick, that means according to the question, the process is in control. Okay, so part 1, we are supposed to test using the 50 computer devices, and the result that we have gotten from our test, we are supposed to try, result that we have gotten from the survey for the 50 samples, we are supposed to test at 5% level of significance whether the process is not in control. So I'm going to, for part 1, I'm going to define my random variable. I'm going to let x be the thickness of the coating, be the thickness of the coating, and I'm going to let mu be x mean, so b is mean. Sorry, hang on for a second, something is like very funny is happening beside me right now, so I need to I really need to laugh. Okay, so sorry. So anyway, I'm back. So so h naught is we are doing a hypothesis testing. So the population mean is, according to the question, 100, and h1, because we are trying to check whether it is not in control. For it to be in control, it cannot be too thin, it cannot be too thick. So for it to be not in control, mu cannot be 100. So it is a two-tailed test. We're not in control. We took a survey of 50 computer devices. So 50, and the sample mean is given to us 103.4 microns. We are going to be stating our test statistics, and in this test statistics we need the population mean and we need the population variance. I don't think you will find it funny, Joyce, because it's okay, I don't even know how to describe, unless you see it, or else it's just not going to be funny. So I'm not going to try, okay, but it's really very funny. Even now I still feel like laughing. I'm going to try to suppress my laughter, okay? So I'm going to focus on hypothesis testing. So I want to state an assumption. I mean, we need to write down the test statistics. We have to write down the test statistics. We need the population mean and we need the population variance. The population variance is given to us as 10 square. Okay, this is the population standard deviation. So according to the question, there's some wear and tear to the mechanical parts. So how do you know that, after wear and tear, that the population variance, population standard deviation or the population variance will remain the same? But we don't really have any other information for us to continue. So I'm going to make an assumption. So I'm going to assume that the standard deviation of x remains unchanged, which means that the population variance that we're talking about here is 10 square. Okay, making use of what that is given to us by the question, it is 10 square. So this will help us to write down the test statistics. The test statistics will be x bar, the mean of 50 samples. This will follow a normal distribution with a mean of 100. I'm taking the population mean, the mean of x. And just like what we talked about just now, here it must be the variance of x, which is 10 square, then divided by the population size, divided by the sample size, which is 50. And since we do not really know what is the distribution of x, so I'm writing down this by the central limit theorem, and this is possible since n, which is equal to 50 here, is large. So So we can definitely write down the standardized version. So it will be Z. If I were to write down the standardized version, it will be X bar minus away 100 divided by square root of 10 square over 50. This follows a normal distribution of 0, 1. So from here, we can press it into our calculator. Using our Texas Instrument calculator, we can press for a z-test. And from the calculator, we'll be extracting out our p-value. So from the calculator, the p-value sorry, what is O value? The p-value is 0.016210. The O value, yeah, I'm going to use the p-value. Oh, okay, I assume you are trying to press P, but you accidentally pressed O because O is beside P. Oh yeah, okay, yeah, it is. We are going to be using our p-value. To be also very honest, I'm not very sure why the standardized version need to be there, but I don't know, I guess it is a little bit like a tradition, because I do see a lot of schools writing down the standardized version, and I'm so scared that if I don't write it down, right, then some of you, if you're to be just writing down the test statistics, you're going to be penalized for your prelim. So I'm not very sure why this needs to be part of the solution. The test statistics, I can understand why, although it doesn't seem to be necessary, but without the test statistics, actually, you cannot be discussing about hypothesis testing at all. So in a way, the test statistics is a display of your understanding of what that is necessary for you to be doing a hypothesis test. But for the standardized version, right, I have always this question and I'm not sure why it is necessary. So I'm just following what I think some schools are doing, okay? And I believe that some of your teachers are also wondering, like, hey, can I remove the standardized version? But what if I remove then Cambridge mark wrong or something? So nobody dare to remove. I'm not sure. But so the p-value is equal to this. And since this p-value, if I were to compare it to the level of significance of 5%, it is less than, so there's sufficient evidence for us to reject. So since p-value is less than 0.05, there is sufficient evidence that the process is not in control. Beacons. Oh, what do you write under H0? But instead they tell us to write under H0. Oh, to write oh, I see, to write the standardized version under H0, right? Actually, the test statistics is very useful. I don't think it is possible for me to just immediately explain to you about it, but the test statistics is like really very, very useful. I'm going to show you why this test statistics is actually very useful in part 2. But I think I was thinking about it, I better answer Joyce, like what is so funny, because suddenly someone is like right beside me right now, like eating. I've never done this before. I'm doing a live streaming halfway and then suddenly somebody is like sitting here beside me while I'm doing math. So anyway, let me show you why the test statistics is very, very useful. Okay, it's like really very useful. For example, in part 2 is actually talking about exactly this same test that we have just done. Okay, and this supervisor wants to check what is the range of the sample mean, what is the range of X bar, such that the process is considered as not in control at 5% level of significance. Okay, and the question gave me 3 marks. Okay, we want to find what exactly is the value of x bar such that the process is considered as not in control. Okay, so I know there are different ways of doing something that is like part 2, but what if I were to try to make use of the test statistics? Because this test statistics govern all the processes of survey that is carried out for a sample of 50. And in part 2, we are talking about a sample of 50 again. Which means, if I were to look at the test statistics, let me show you what I will do for part 2, okay? If I can just base on the test statistics, we are going to be looking at a bell curve since it's a normal distribution. So this is going to be x bar. According to my test statistics, here is 100, right? And since we are looking at a two-tail test of 5% level of significance, so I know on the left-hand side here, this is going to be 0.05 divided by 2. And this here will also be 0.05 divided by 2. Okay, so we have this. And this is the critical region, which means that anything that falls within here, it represents that the process is not in control, correct? So what I'm going to try do is to find this value and this value, which means that as long as x bar, whatever it is less than this value, or when x bar is more than this value, then it is not in control. Okay, so we are talking about, yes, we are talking about we are talking about H0 being rejected. I am not sure whether in the presentation you got to write H0 to be rejected for this. I mean, to play safe, I guess it is still good if you can do some explanation to your solution. So okay, let me write down for H0 to be rejected. For H0 to be rejected, I know x bar must be somewhere that is within this region, or x bar must be somewhere that is within this region. And we are making use of the test statistics. And you know what we can do for those of you who are using the new graphing calculator? You can just simply press this into your calculator. Let me show you. You can press this into your calculator and you're going to get the answer as this. Hang on, let me just pull up the screenshots. Oh, nice. It's just like above me. So you can just press this into the calculator. Okay, you press this in the calculator, the region is going to be the region that is here. And since we are talking about this value and this value being symmetrical about 100, and so they are the same distance away from 100, this area here is 1 minus 0.05, mu is 100, sigma is going to be square root of this whole thing. We are talking about this region that is here, so I choose center, paste, inverse norm, I press, that means, right, I know that these two values are here. So for H0 to be rejected, as long as this is going to be less than this value, which is, if I were to round off, if I were to round down, it is this 0.2, or x bar must be bigger or equal to this value, which is 2.8. And let's make sure the x bar, which is the quoting, should be a number that cannot be negative, cannot be 0 or negative, or else there will be no quoting, right? So I'm going to add in this extra 0. Okay, and that is the power of you acknowledging the test statistics, because it actually governs everything that is calculated from this point onwards. From p-value to this x bar to the critical region, everything is governed by the test statistics. And so I do see a purpose of writing down these test statistics, although our calculator has given us a lot of convenience. But writing down the test statistics is a reminder to me, at least, that everything is calculated based on this So it reminds me of how the p-value is being calculated. It reminds me that in a question that is like part 2, you know, if I can just visualize it on a bell curve that is based on the test statistics, my solution is so short for a 3 marks question. To me, this is fantastic. Next, part 3. Part 3, we are supposed to find the unbiased estimate based on these 40 devices. We are supposed to find the unbiased estimate of the population mean and the population variance. So the unbiased of the population mean. For the way the data is given, the unbiased estimate of the population mean will be summation of y minus away 100 divided by the sample size 40 plus 100. I'm using the formula that I put inside the Achevas TV theory outline. So we have a 164 over 40 plus 100. This is equal to 1041 over 10. We're going to find the unbiased estimate of the population variance. And I'm going to once again make use of the formula that is on the Achevas TV. So this is going to be 1 over n minus 1. Then summation of y minus 100 square minus away summation of y minus 100 square divided by 40. So this is equal to 1 over 40 minus 1. This is 9447. Minus away, this is 164 square over 40. So this, I will be getting a 43873 over 195. 195, yeah, 195. We unbiased estimate to the population mean and the unbiased estimate to the population variance. Let me write them down here. So this, I will need the numbers in a little while, so let me record it down here first. And for the unbiased estimate for the population variance, it is 43873 over 195. And in part 4, in the context of this question, give a reason why we may not be able to use 10 microns for the standard deviation. And I guess it is the same reason as what we have assumed just now. We have assumed that the standard deviation remains the same. We have assumed that the standard deviation remains the same. But for here, one reason why we may not be able to use this standard deviation that is already given to us is, let me just write it down here, okay? So the standard deviation may have changed due to the wearing out of the mechanical parts. So the actual standard deviation, maybe I should write down the word population. The actual population standard deviation may have changed. Just now we assumed that it was the same, may have changed due to wear and tear. Oh, due to okay, should I write? Due to the wearing out of the mechanical parts. Okay, then for part 5, assuming that the standard deviation has changed, goodness, it is giving me the same the same hint for part 2. As for part 1, just in case we didn't manage to come up with this assumption, reading part 4 and part 5 probably hint to us that standard deviation is the one that we can make use of to answer this. So assuming that the standard deviation has changed, we want to test at 4% level of significance whether the process is not in control. So we're going to carry out the test one more time, where h0 is such that mu is equal to 100. h1 is such that mu is not equal to 100. And this time we are looking at sample size of 40. The sample mean, just now we have already found, it is 1041 divided by 10. And as for the population variance, since it may have changed, I'm going to make use of the unbiased estimate to the population variance, and this is 43873. Okay, the one that we have calculated just now, this divided by 195. So the test statistics that we are going to be working on will be an X bar as one that follows a normal distribution with a mean of 100 and a variance of 43873 divided by 195, and this is going to be divided by the sample size 40, and we are writing, oops, I shouldn't use X, we should use Y, so Y bar. So this is done by the central limit theorem. Since n in this case is 40, I'm considering this as a number that is considerably large also. And I'm going to write down Z with a standardized version. So this minus away 100 divided by square root of 43873 over 195 divided by 40. This follows a normal distribution of 0, 1. Again, I'm going to try to press this into the GC to get the p-value. This time the p-value will be 0.083854. We are talking about 4% level of significance. So since this p-value is more than 0.04, this time there is insufficient evidence. That the process is not in control. Insufficient evidence that the process is not in control at 4% level of significance. This I'm really not sure, because it is actually still a possible assumption to make because you are combining a lot of different x's together. So x1 plus x2 all the way to x50 divided by 50. So to do this combination, you will indeed require the coatings to be independent of each other, but not the average coating that must be independent of each other, but the coating must be independent of each other. So it is not x bar that must be independent, it must be x that is independent of each other. Okay, that is the difference. Okay, so if you say x is independent of each other, I think there may still be a slight chance that you're going to get marks for it. If you were to say the average coating, there will be no chance for you to get marks for it. But to reduce the risk for part 1, I think it is still safer actually to talk about the standard deviation. Okay, because let me see, has the question mentioned that there's okay, the question actually didn't mention about x being independent, but it is, I feel that it is a little bit risky. Yeah, I'll still go for variance to be assumed to be the same. In fact, there was one year, I cannot really remember which year. There was one year when Cambridge actually asked something that is like this. They asked for an assumption for the variance. No, the variance is 1 over the variance n over, oh, no. Okay, I think Joyce, I know what you are trying to talk about. You are talking about another formula. You're talking about s square being n over n minus 1 of the sample mean, sample variance. Okay, so it is this formula. But we have already calculated s square, which was from the previous part, the unbiased estimate to the population variance. So if you are talking about n over n minus 1, it was actually a formula that is used before you get the unbiased estimate. So it is actually this formula. Okay, and this that is here is the sample variance. Okay, this one is the sample variance. Okay, then you will be using this n over n minus 1. Oh, as in like giving a definition for y, right? I was also thinking about it, because like, for example, in the first part, the thing is, if I didn't define x, I think for some of the prelim, we may be penalized, because we didn't define x. But then the second part of the question, they actually came up with y, but there was no definition for y. So I was also thinking, should we define y? Because it is not me who came up with y, it was actually the question that gave y. So I don't have a proper answer for this. For me, I'll probably not define, since it's already given to me by the question. Whatever that is not given to me by the question, I'll probably then try to do some definition. The difference between the first part and the last part is number one, the sample mean is different. Right, the sample mean is different. Yeah. Sample mean is different. Okay, but of course I don't think you are talking about the sample. Okay, I mean the sample mean and the sample size, they are different, but the main difference is actually this, where in the first part you are using the historical standard deviation, the historical population standard deviation. But because now in the last part you are starting to suspect that wear and tear of the mechanical part actually caused the standard deviation, cause the population standard deviation to change. That's why you are not using the 10 microns anymore. You are coming out with an unbiased estimate based on the freshest data, based on the new set of data that is being collected. Is there a need to divide p-value by 2 here? Because no, to divide p-value by 2, because it's not equal, because of the not equal sign. No. Okay, p-value is not the okay, I will suggest that okay, first of all, you shouldn't be dividing p-value by 2, because number one, p-value is not probability. Where p-value is definitely related to the probability, a probability that is also related to the sample mean, but p-value is not the probability. Where p-value is in fact the number that your calculator has given to you, so they can use it to compare to the level of significance directly, regardless of whether it is a one-tailed test or a two-tailed test. So p-value, it is already properly calculated, so they can always compare to the level of significance directly. But for you who have asked this question, right, I believe that you have some problem in knowing what exactly p-value is. I mean, how p-value is being calculated. I really suggest that you go and find out like how p-value is calculated for a one-tailed test, how p-value is calculated for a two-tailed test, and how in general the p-value by itself, regardless of the one or two-tailed test, is a number that you can use to compare to the level of significance directly. Or else, if you don't check it out now, because one problem with hypothesis test is the idea that is behind that governs everything. where you don't need to know in depth into that about the ideas, but if you don't try to find out now, most likely you will have even more motivation to find out about it before your A-levels, and you really don't want question that is like this cause you to have a lot of confusion for hypothesis testing. So I would suggest that try to go and check it out now. It is not just the question that you are specifically the question that you are asking now, but go and check out how p-value is being calculated for a one-tailed test and a two-tailed test. And Alvin, how is today's live stream different from other days live stream? Why is today's live stream a nice live stream? Use the actual definition of p-value. Many times we try to many times we try to define the level of significance. But for p-value, if you go and look at your school's notes, some of the school's lecture notes actually define p-value. They define p-value based on the rejection of H0. So for example, to reject H0, at for example, to reject H0 at for example 100%, sorry, for example 100 alpha percent level of significance, to reject H0 at 100% level of significance, we just need to make sure that p-value, okay, independent of whether it is a one-tail or two-tail test, okay, we just need to make sure that the p-value is less than alpha. Okay, so if we can just look at this again from another perspective, it is just saying that alpha must be bigger than the p-value. Or like for example, in this case here, the p-value is this number, right? So in order for us to reject H0, alpha must be bigger than 0.083854. So the p-value, which is this number here, is defined, if you were to check your lecture notes, the p-value is defined as the smallest level of significance such that H0 is going to be rejected. With the smallest level of significance, because alpha, which is the level of significance, must be bigger than the p-value. So it is defined as the smallest level of significance such that H0 is going to be rejected. In fact, for some of you who are in my tuition class this week, I'm actually going to be asking you this. Okay, what is the, because we have talked about the definition of p-values, I think twice in our tuition class, and so I'm planning to ask you guys this week during the class. Okay, like, can you still remember what is the definition of p-value? Because most likely everyone will remember the definition of the level of significance, but no one will remember the definition of p-value. I'm not scared that the school will ask. I'm scared that A-level will ask. Okay, so if you have forgotten, take a look at your school's notes again. I believe it is going to be inside your notes.